Welcome to Chapter 4. Today, we're stepping into the world of stochastic processes. Up until now, we've focused largely on single random variables or static distributions. In this chapter, we'll explore how randomness evolves over time, which is the cornerstone of understanding real-world signals and systems. Let's start with the basic notion of a stochastic process. Think of it as a collection of functions. If we look at a single realization or one specific run of the experiment, we get a deterministic signal over time. However, if we freeze time at a specific instant, say ti, the value we see across all possible realizations is actually a random variable with its own probability density function. So, a random process is essentially a function of both time and the underlying random outcome. To visualize this, imagine a series of signals, x1 through xn, layered on top of each other. At any specific point on the timeline, like t1, we can slice through these signals to see a distribution of values. This vertical slice represents the random variable x at that moment, allowing us to calculate statistical properties like the mean or variance specifically for that point in time. A critical concept in signal processing is wide-sense stationarity, or WSS. A process is WSS if its statistical properties don't change just because we shift our starting point in time. Specifically, the mean must be a constant, and the autocorrelation must depend only on the time difference, the lag, between 2 points rather than their absolute positions. While a second-order stationary process is always WSS, remember that the reverse isn't always true. Let's dive deeper into the autocorrelation function for these stationary processes. Since the timing depends only on the difference, tau, we can define the autocorrelation Rx as the expected value of x at time t multiplied by x at time t plus tau. This reflects how a signal correlates with a shifted version of itself. Similarly, we can define the autocovariance, which is essentially the autocorrelation minus the square of the mean. The math leads us to some interesting symmetry. If the mean is 0, the autocovariance and autocorrelation become identical. By normalizing this, we get the correlation coefficient. One of the most important properties to remember is that the autocorrelation function is symmetrical. Rx of tau is the same as Rx of negative tau. This means the relationship between 2 points depends on the distance between them, regardless of which direction you move along the timeline. What happens when the time lag is 0? At tau equals 0, we are comparing the signal to itself at the exact same moment. This gives us the mean square value, which represents the total power of the signal. In this case, the correlation coefficient is always 1, and for any other lag, the absolute value of the correlation will never exceed this maximum value at 0. This graph illustrates a typical autocorrelation function for a stationary process. Notice how it peaks at 0, representing the maximum correlation, and generally decays as the time lag increases. This visualizes how the signal gradually forgets its previous state as time moves forward, eventually settling toward the square of the mean. Now we encounter ergodicity. This is a powerful property where we can swap statistical averages, which require many realizations, with temporal averages, which only require one realization over a long time. For an ergodic process, calculating the mean by looking at one signal over a long duration gives the same result as looking at the entire ensemble of signals at a single moment. This is incredibly practical for real-world measurements. This table summarizes the equivalence between statistical and temporal averages under ergodicity. Whether you're looking for the standard deviation, autocorrelation, or autocovariance, ergodicity allows us to use time-based integrals of a single sample to find the underlying statistical parameters of the whole process. This simplifies our data collection significantly. To visualize the difference, a moyenne d'ensemble or ensemble average looks vertically across all possible signal realizations at one time, while a moyenne temporelle or time average looks horizontally across a single signal over a long duration. In an ergodic system, these two views provide the exact same information. Let's look at some specific examples, starting with the Gaussian process. This is perhaps the most famous type because it models so many natural phenomena. In a Gaussian process, Any collection of samples taken at different times will follow a joint Gaussian distribution. Mathematically, we represent these samples as a vector from x1 to xn. Each point in time has an associated mean, and together they form a mean vector. This structure allows us to describe the entire multidimensional distribution using just the means and the relationships between the points. If these Gaussian variables are independent, their joint probability density function is simply the product of their individual densities. The formula shown here might look complex, but it essentially describes a multidimensional bell curve, where the probability is determined by how far each point is from its expected mean. When a Gaussian process is also wide-sense stationary, the mean and variance are constant across all samples. A unique property of Gaussian variables is that being uncorrelated, having a correlation of 0, automatically implies they are independent. This is a special characteristic not necessarily found in other types of distributions. A classic example is Gaussian white noise, often found in electronic receivers as thermal noise. It's called white because its power spectral density is flat across all frequencies, much like white light. Because its autocorrelation is a delta function, it means that any two different samples, no matter how close they are in time, are completely uncorrelated and independent. Next, we have the Markov process. This describes a system with no memory. Specifically, the future state depends only on the current state and is completely independent of the past. If you know where the process is right now, knowing how it got there provides no additional information about where it's going next. When these states are discrete, we call them Markov chain. The telegraph signal is a great way to think about information sources. In Morse code, the sequence of dots, dashes, and spaces can be modeled as a process where the probability of the next symbol depends on the current state of the message, fitting the framework of Markovian modeling. Moving on to the Bernoulli process, we start with the simplest building block, the Bernoulli random variable. It has only two possible outcomes, usually 1 and 0, representing success or failure, with probabilities P and Q. This is essentially the mathematical model for a single coin flip. A Bernoulli process is just a sequence of these independent trials over discrete time steps. You can see it here as a series of binary pulses. Its probability density is a combination of two delta functions, representing the two possible values the process can take at any given step. If we start summing up these Bernoulli trials, we get a binomial process. Here, S, N, represents the total number of successes or ones that have occurred up to time n. This shifts our focus from individual events to the cumulative total over time. The probability of having exactly k successes in n trials is given by the binomial distribution formula. This uses the n choose k combination multiplied by the probabilities of success and failure. It tells us the likelihood of reaching a specific cumulative state after a certain number of steps. While Bernoulli and binomial processes happen in discrete time, the Poisson process occurs in continuous time. It's the perfect model for counting random occurrences over a duration, such as people walking into a post office or telephone calls hitting a switchboard. In a Poisson process, the probability of seeing exactly k events in a time interval depends on the average rate, lambda. One key property is that events happening in non-overlapping time intervals are independent of each other. We define the process x, t, as the total count of events from time 0 up to time t. This final visualization shows a Poisson process in action. The events occur at random points along the continuous time axis, and the process counts them, creating a staircase-like graph that increases whenever an event occurs. This concludes our overview of these fundamental stochastic processes and their behaviors.